Bob was saying that they're using tanks for the Bunsen burner type of equipment down there. That's cool that there's nothing
Right.
in there.
So when I started designing labs 20 years ago, it was very common to bring natural gas into the building. You would use it to fire a boiler and get hot water. You'd then take a tap off and you'd run it through the lab, and you would have natural gas at all the benches.
Mm-hmm.
So, but if you go to these old chemistry and biology buildings, hardly anybody's using them, or just a select few. So they were spending a lot of money for the piping. Their code almost a decade ago, put in that you had to have the isolation in case there was a fire. You could shut off that lab, so you'd end up with a box with an isolation valve in the wall, which architects never liked because they're not aesthetically pleasing. And there's always never really a good place to put them. And the use is just low. So why put all that money in for piping that is hardly ever used? So they make laboratory size bottles, and then they also make K and C size cylinders. So on the lab benches, there are places that they can rack up bottles and use gas right there if they need it.
Okay.
But most of the science is moving away from an open flame work. They'll go to a heat gun or a hot plate to do their work instead of a flame. This is where the two energy storage tanks are.
Okay.
So this is a manhole, and that is a manhole, and so this represents one tank. And then you'll see there's another plate over there, and a further one over there. That's the second tank. Each tank is, 25,000 gallons, and they're interconnected. So the cold water comes in on one side, runs through the tank. You can see where the manhole is. That's the connection to the second tank, and then goes to the far tank, and that's the hot side of the tank. So when we generate hot water, we put it into that side of the tank. When we generate cool water, we put it into this side of the tank. And that boundary layer between hot and cold will adjust over time. So in the morning, it should be mostly cold. And then as that cold water is used up, it's replaced with hot water. And then at night, that hot water is discharged and again filled up with cold water. But this was quite an adventure. And 25,000 gallons is the largest size you can get on a flatbed truck that's ASME rated, because to build a tank out on the site would be astronomically expensive. So when we do these, it's kind of 25,000 gallon increments. So this is the freezer farm. And so you can see the freezers lined up here, and then above on the top, you can see the chill water supply and return that come down, basically grab the heat from the freezers and then put that back into the thermal storage tank. We have backup upon backup on this, so because this is a key piece of their research, they can't lose these samples. So if the main chill water system goes down, we basically isolate everything else, and we just use the thermal storage tank capacity for this cooling. If there is a need that they somehow go multiple days without being back up online for some reason, they can actually run domestic water through this. We don't want them to do that. We make it very difficult for them to do that. They actually have to insert pipe sections. So up behind those air handlers, there's actually sections of pipe that they have to connect and hose that they have to do, because we don't want them to use one through cooling for water, but we need to keep the samples safe. So it's basically that third layer of protection. And before they get to that, ideally they would move it to another site. So if they really see that, hopefully they would move things before they get to that.
And I would assume something at -80 would keep long enough to ship it down the road.
Yes, yeah, especially in a refrigerated truck. So this is one of my favorite kind of shots because it shows how well daylighting was done. So it's a fairly cloudy day here in San Diego, and you can see on the north side of the lab, that light fixture is off. The centerpiece, the center two fixtures are on, and again, the south side is off. So we're getting enough daylight bounce coming in from the south side, and we're getting enough reflection off these walls to come back in to actually light those without needing any artificial light at all. So that's, and on a sunny day, none of these lights will be on. And we were here on a tour, I think it was like 6:30 at night, and people were still working, no lights were on. And it was just fantastic.
That's great.
Yeah.
So even the power is coming from the ceiling in here.
Yes.
With all of these kind of cords.
So that's been another big change in science. It used to be that everything was fixed casework. And then as soon as another user came in, they wanted new casework, and it was very expensive to rip all that out, put all the floor back in, and change it. So you'll see it's actually, nothing is fixed, it's all just tables. Everything else is on casters and slides underneath as they need it. And then they're getting power and data from this. They didn't have very many central gas services needed, but you can actually connect gas to those ceiling panels also.
Oh, wow.
And so normal and emergency power is there, and then also the green plugs. So we'll see if we can see it. So that's an emergency circuit.
Okay.
So if they lose power, it'll come back on.
Okay.
This is a green plug, so they know whatever this is connected to, which just looks like this pipette, that will turn off at night and not draw power.
Oh, wow. So the red is 24/7, basically.
There's power.
The
Yeah.
green is scheduled.
Yep. These are part of the air acuity system also. So if the user makes a spill and they know something's wrong, they can hit this button and increase the ventilation rate. So this manhole here, this is our 5,000 gallon tank. So all the rainwater that comes off the roof on the north side of the building actually goes out to that cistern that's outside the building, put in by the civil engineer. Everything on the south side actually flows into this 5,000 gallon tank. And anything on the site on the east side goes into that first cistern, drains into the second cistern, and then fills into here. So it just cascades through. And then from here, in that room down there is where we have the pumping station. So there's a set of pumps here, pumps water into there, and there's UV filtration, particulate filtration, and then that is where it's distributed out to the various places in the building.
So these are just simple overflow from one 45,000 to another 45,000 to this 5,000, or however that breakdown is.
I think it's like 30 and 60, but in essence, yes.
30 and 60, and then all the filtration still come from this 5,000 gallon tank into that.
Not all the filtration. That's why I wanted to show you this. So here's your storm drain coming in. It goes through this storm drain filter, and it removes that big stuff. And then from there it flows out. We actually have a finer filter available, get a bit more of the particulate out, and then that goes over to the drain.
Okay.
And then that pumping station is even finer filtration. So by taking the big stuff out, we keep the maintenance on those pumps down because they're hard to get to. They're submerged.
Right.
So you'd have to isolate the tank, pump it out, send somebody down into a confined space. We want to minimize that, so we do this pre-treatment as much as we can.
And this is easy to access for a maintenance
Right.
person.
This is actually in case you get 200-year storms in a row.
Oh, okay.
So there's actually an overflow from the civil cistern. So if that starts to overflow, but if for some reason that doesn't work for some reason, this is the overflow from this tank. So
Oh, so this would go out to the storm
out
drain.
to the storm drain and out the
Okay.
building. Yeah.
This is the worst case scenario from a storm event.
Right, right. Because it doesn't take too many feet in elevation that water pressure actually has a pretty catastrophic effect. And actually they put, in one of these, I think it was that one over there, they put the wrong filter piece in, and so it couldn't drain fast enough.
Oh, wow.
And they showed us video where water was just shooting out of the side because it had backed up into that filter. They put the right filter housing in and it worked just like we designed it. But yeah, we don't want that pressure to push up a manhole or things like that.
Right. Yeah, find that path of least resistance for water.
Yeah.
Right.
The other thing you'll see is we painted down here everything white. So typically cement and dark colored areas are going to absorb light, and so you have to put more lighting power out there to achieve the same lumen quality, lighting level. So what we did here is by painting everything white, including the pipes and whatnot, the light reflects and bounces better. So we're actually at a lower watts per square foot just in general lighting, but it also just provides a nice, safer environment. So the central core will stay on. You can see she pulled over there, so those lights are on. And if we were to walk, those lights should start to come on. But again, all well lit. And then the last bit is, because we're on a slope, part of this is below grade. You can actually see the plantings right outside there. We didn't want to have to ventilate a garage, and if you stick a garage below grade, you have to ventilate it, and that's fan energy and things like that. So we work with ZGF. There's 2 criteria you have to meet. So much percentage of the exterior has to be open, and then so many square foots per parking space. And so we work with ZGF to make sure we got enough square foot of opening on both sides so you can feel the breeze coming through here, so there's no need for a fan to ventilate the space. But by hitting that ratio, there's no fan, so there's no energy. So
That's great.
teamwork making it pull energy out.